Hi, I'm Chris Johansson.
I'm Caleb Rye.
And I'm Taylor Dark, and we are project31, the Wi-Fi speaker and streaming host. The main objective of this project is to create a system which can enable devices with an internet browser, like a smartphone, laptop, etc., to control a home stereo setup using a local area network media server. The presentation will cover the three main aspects of this project: the server, the networking, and the hardware, as well as the top-level block diagram. The system will have multiple satellite devices which will communicate with the server, then play the audio out to speakers connected to the satellite. Audio output will be controlled with a web page that depends on a pre-existing software to eliminate platform differences. Wi-Fi will be used to connect these satellites, allowing them to be placed in any area of the average home. The satellites will be able to be controlled individually, and the server will also be able to play music from multiple sources, including music stored on other network devices. Each speaker will be individually controllable by the device, allowing the customer to play different music in different rooms at the same time.
The system has three external inputs: AC power, environment, and user input. The AC power is regulated through a power supply that will convert it to DC power, which will in turn supply all components in each satellite. User input is accepted in the form of a web page GUI. From this input, the system is required to run Python scripts hosted on the server. These scripts will control the transfer of data from server to Wi-Fi module. This data will be the information for controlling the playback and also the actual digital music files. The server will communicate back with the web page GUI in the form of visual feedback, showing the user what is playing and on what speakers. Once the control data and audio files are sent to the satellites, it is processed by the microcontroller, and the audio is stored in an external memory for a buffer. This data can be recalled from storage and sent to an audio output stage to be decoded and transmitted as an audio signal to the user's speakers. The outputs for the system are visual feedback from the GUI to the user, and the output audio signal from the satellite. Environment is listed as an input because of the temperature the system is running in, but it is not listed as an output because the satellites do not affect the outside environment as a standalone system.
The first major aspect of the project is the server. A Raspberry Pi was selected to act as the server for the project as a cheap Linux machine to run Python scripts and communicate with the satellites. The Raspberry Pi was chosen for many reasons. It has an SD card, so it is more versatile in changing the amount of memory should the project grow. It is also very accessible, cost-efficient, and portable. Plus, because it's Linux-based, it is very easy to script and is open source, providing a lot more freedom. The Raspberry Pi will send information back from the satellites on their state to be shown to the user. A website will be created for the users to both manage their music libraries and control the satellites. Users will be given a website profile where they can store the music they uploaded to the server in preferred playlists. They can either upload or remove one song at a time or several songs at once. The user will pre-select their desired songs from the library via checkboxes and submit. The new playlist will then also show up in the GUI ready to be utilized. There will also be checkboxes corresponding to the satellites being controlled by the system. That way, the user can turn individual satellites on and off easily while music is in play. The other main components of the website are more or less those of a simple music player GUI. There will be buttons for play, pause, skip forward, skip backward, and shuffle, as well as a go-to search function. The website will be done in Python and PHP and will be very data structure heavy.
The second major component of the project is networking. The goal is to be able to create a system in which up to 20 satellite units, spread across a household, could be streaming data from the media server. In addition to this challenge, there should not be significant buffer times when playing new songs, meaning that the bandwidth must be well utilized to ensure immediate and high-quality playback. The system will use wireless protocol 802.11g. 802.11g wireless is capable of communicating at speeds of up to 54 megabits per second at ranges of up to 150 feet in buildings or 300 feet in open areas. The ranges of 802.11g have been shown to provide good coverage for most households and should be sufficient for most home audio systems that would make use of this project. Just as important as the range of the connection is the speed. At a theoretical max of 54 megabits per second, or 6.75 megabytes per second, wireless communication on 802.11g is fast, but nowhere near as fast as wired connections. This places some constraints on the audio that the system will be able to play. Many consumers dislike low bitrate audio. Ideally, any home audio system would be able to support lossless encoding, allowing for very near perfect audio reproduction. Unfortunately, lossless file formats are quite large. As a compromise between quality and file size, the goal of this project is to be able to stream 256 kilobit per second MP3 files, which are of good but not lossless quality. While file size varies based on the complexity of the song, preliminary testing shows that each audio stream will consume less than 320 kilobits per second of bandwidth. If all 20 satellites are streaming, this equates to 800 kilobytes per second on the server, which is well under 6.75 megabytes per second, which is the theoretical max. This should leave plenty of time for transferring control and state signals in addition to the media. In order to ensure that buffering time is minimal, the User Datagram Protocol, or UDP, will be used to transfer files being used for immediate playback. UDP allows for rapid transfer of files and for playback to start immediately, but does not have error correction. The satellites will be able to buffer several songs in advance, provided a playlist is selected. When a song is buffered to the satellite ahead of being played, Transmission Control Protocol, or TCP, will be used, which will allow for error checking to ensure that the media on the device is a perfect copy.
The final major aspect of the project is hardware. The hardware consists of the Raspberry Pi server and the individual satellites. These satellites consist of a Wi-Fi module, a microcontroller, external memory, and a power supply. Between the server and each satellite, there will be 3 signals of communication. These are control, audio, and state. The control data, which is the user's input to the system, is sent from the server side and received by a Wi-Fi module. Audio data is also received from the server, and this data contains the song that is being sent to the satellite. This can either be the song currently playing or the one that's being written to the buffer. The Wi-Fi module is responsible for receiving the packets from the server and relaying them via Serial Peripheral Interface Bus, also known as SPI, to the microcontroller. Another requirement of the Wi-Fi module is to receive feedback from the microcontroller regarding the state of playback, so that the server knows what is happening on the satellites and can respond accordingly. The state signal will act as this feedback, informing the server if something is playing, and if so, what is playing. 3 lines of communication are present between the Wi-Fi module and microcontroller. The microcontroller's purpose is to process all the data that comes from Wi-Fi. The 2 data lines, control and audio, are received from the Wi-Fi module, and from there, control data will tell the microcontroller when to play or stop and which songs should be playing. The audio data is processed and then output to the buffer to be stored. The external memory is serial connected and will act as storage for the buffer. The extra memory will be sufficient enough to hold several songs worth of audio data. When this data is needed, it is retrieved from the buffer and sent to an audio output stage. The purpose of this stage is to decode the digital audio information and output the audio signal that can be played through the speakers connected to the satellite's 3.5mm jack. The project is intended to be fully modular, so there will be no speaker portion of the hardware. The user can simply plug each satellite into the wall and then connect their own speaker set into the 3.5mm jack on the satellite. The power for each component in the satellite will be powered by one power supply. This power supply takes 120 volts AC at 60 Hz from the wall and rectifies it and then steps it down to 3.3 volts DC. The satellites will not draw more than 700 milliamps of current from the power supply.
This presentation covered the main components and ideas of Project 31, the Wi-Fi speaker and server, those being the network, the server, and the hardware we use to make it all. As new technology comes down in price and increases in accessibility, the demand for home products with more advanced integration and compatibility continues to grow. This project aims to bring together existing technology and create a product that is widely compatible, easy to use, fun, and and above all, loud. So cue up some tracks and rock on.